Okay, this other worksheet is just a bunch more examples, and I'm going to go through them fairly quickly here. On each one, we're again just taking the limit and seeing what happens. Okay, this first one, I'm gonna circle the dominant terms and then just write the answer. This is going to be converge to a half. This is the dominant term, and down here, this is the dominant term, because in both cases, the dominant terms are the exponentials. So we've got 3 to the n over 2 to the n. That's going to, 3 is bigger than 2, so this is going to diverge to infinity. Okay, the dominant term here is 4 to the n. Dominant term down here is 1.001 to the n. So we've got a polynomial over an exponential. So this is going to converge to 0. Now, if you were to graph this one, it would take a long time for it to get to 0. It would converge slowly because this exponential down here is just a little bit, the base is just a little bit bigger than 1. So it would take a long time, but it would eventually converge to 0. This next one is also a really slow function. On top, you've got a, on top you've got a polynomial, and on the bottom you've got an exponential. Now that's a polynomial with an exponent of 100,000. This thing is going to converge to 0 because the exponential is going to grow faster, but it's going to take it a really, really long time to do so. In fact, if you were to graph this, it would look like it's going to infinity because you'd have to get out to a really huge n before it starts to drop off. But eventually this would go to 0. All right, about down here, e to the n, down here you've got 3 to the n. Actually, you've got negative 3 to the n. Those are our dominant terms. So if you think about this, it's essentially going to be e over negative 3 to the n. Now, e is less than 3, so this is going to converge to 0. Okay, factorials. On our rabbit and turtle chart, remember, factorials grow faster. Factorials grow faster than everything except for n to the n. Is that completely true? There might be some other functions that grow faster, but as far as things we're going to encounter in this class, n to the n is the only thing that's going to beat factorial. So let's look at this one. N factorial over 10 to the n. This is going to be faster. So this is going to diverge to infinity. And just for fun, let's do another one over here. If you had a sub n is n factorial on the bottom, and you had, say, 20 raised to the n on top, this would converge to 0. Because the factorial is going to outrun the 20 to the n. Okay, this one's interesting because you've got n plus 1 factorial over n plus 2 factorial. So how can you deal with this? Well, here's the thing. Factorial is 1 times 2 times 3 times up to n, or whatever your number is that you're looking at. So let's take this over here and factor these out. N plus 1 factorial, you got n plus 1 times n minus 1 over down here you got n plus 2 times n plus 1 times n minus 1 times that. So if you come up here and start canceling things, n plus 1 is going to cancel with that. Basically, everything's going to cancel out except for this term here, n plus 2. So you've got to ask yourself, what happens to 1 over n plus 2 when n goes to infinity? And the answer is that goes to 0. All right, 3 over n plus 4. That one seems easy after all these other ones. 3 stays at 3, n plus 4 goes to infinity, so this is going to converge to 0. Sign in. Sign in, is just going to be various values from here. But they're going to kind of jump around. So they never settle down to anything. So this is going to diverge because it oscillates. Or maybe I shouldn't say oscillate, because oscillate implies that it's going between a couple of different values. It diverges because it's I don't know, I guess you could say it's erratic or jumpy. All right, sine n over n. Okay, this one, the sign is going to stay between -1 and 1, and this is going to go to infinity. So if the bottom goes to infinity, this is going to converge to 0. All right, 11 and 12. We've got cosine pi n and sine pi n. Now these are a little bit, they look like they'd be the same, but they're not quite. If you do cosine pi n, cosine looks like this. And if you look at the multiples of pi, that's going to be, let's see, here, here, here. Let's draw a little more. Not being very symmetric here. But basically it's going to be, but wait a second, I got that wrong. For cosine, the multiples of n are going to be, the multiples of pi n are going to be, let's see, here at 0, which I should mark up here. This is at 2 pi. This is at 4 pi. That's at 6 pi. And at the odd multiples are going to be there. So cosine is going to bounce between 1 and -1. So this is going to diverge because it does oscillate between -1 and 1. Now sine pi n, if we graph sine, that's going to be here, here. It's going to be all these values. So this one converges to 0. And that's a very simple way of converging. It just always is 0. So sine pi n converges to 0, and cosine pi n diverges because it just jumps back and forth between 1 and -1. All right, let's just do one more of these. I want to talk about this one. Inverse tan of n. If you graph inverse tan, it looks like this. It's got a horizontal asymptote at pi over 2. So 15 here is going to converge to pi over 2. All right, I think that's enough of these.